Hello dear students, welcome to my channel again after so many days. So today we'll begin with a new chapter and the chapter's name is circles. Okay, so before we begin with the exercise 17a, I would like to mention few theorems in front of you. Okay, and please make a note of those theorem in your copy as well. Okay, so let us begin. Okay, so theorems on circles. So the first theorem that we are going to learn here is this one. The angle subtended by an arc of a circle at the center is double the angle subtended by it at any point on the remaining part of the circle. Now in order to understand this particular theorem, we'll take three different cases out here. Okay, so according to question, the angle subtended by the arc of a circle. So let me take one arc. So from this circle, this AB, okay, so I'm taking the arc AB. So this is the arc. Okay, so here the arc is the bigger one, right? Okay, so I've taken the arc AB, okay, and the angle subtended by the arc, that means this is the arc and the angle subtended by this arc with the center is, this is my center. Okay, so this is the angle subtended by this arc. Okay, similarly here the angle is this one, angle subtended by arc AB is this one. Okay, and similarly the angle subtended by this arc AB with center will be this one. Okay, so this whole angle, that is the reflex angle. Reflex angle means the angles which is greater than 180 degrees known as reflex angle. So here this angle AOB, reflex angle AOB is the angle subtended by arc AB here. Okay, and here according to the theorem, this angle subtended by the arc at the center will be double the angle subtended by it at any point on the remaining part of the circle. That means apart from this arc, let me choose any point on the remaining part of the circle. Okay, so apart from this arc, I have chosen point C in the remaining part. Okay, now in this case also this is my arc. Okay, and I have chosen one point P on the remaining part. Okay, on the remaining part I have chosen P here. Okay, and this was the arc here, right? And the remaining part is this part here, right? So in the remaining part I have chosen one point P. Okay, please make note that this is not C, this is P. Okay, everywhere I have taken P, so this is also my P here. Fine. Okay, now according to this theorem, this angle subtended at the center will be double the angle subtended by it at any point on the remaining part of the circle. That means ACB is smaller than this. Okay, so which is clearly seen from the figure, that is APB, that is APB is just half of this, right? Because this is bigger, similarly this is bigger, right? So according to this theorem, we have angle AOB equals to twice angle APB. Fine. Okay, let us move on to the next theorem. So theorem says angles in the same segment of circle are equal. Okay, so in order to understand this, we'll take this. Okay, so I have chosen one segment AB. Okay, so this AB is one segment. Actually I have not drawn this line, but you have to imagine that there is a line joining A and B. Okay, so AB is a chord which divides the circle into two segments. Okay, so from here I have drawn two angles in the remaining part, that is ACB and ADB. Okay, so according to this theorem, this angle and this angle has to be equal to each other. That means angle ACB must be equals to angle ADB. That is ACB is this angle and ADB is this angle. Okay, so that's what the theorem says. Now let us try to apply this theorem in the given diagram, that is this diagram. Okay, now if you see here, the diagram clearly shows that these two angles must be equal. How? Because if I take this as a segment, that's CB, okay, then in the remaining part I have drawn 2 points, okay, and I have just joined them, okay. So that means these two has to be exactly equal. Now similarly, if I join these two, then these two are 2 points in the remaining part of the circle, okay. So that's why this and this both has to be equal to each other. Fine. That is CAB, that is this angle is equal to CDB, that is CDB, this angle, and we have ACD, that is this angle, equals to ABD, that is ABD, this one, okay. So you may pause the video to note down. Okay, now let us move on to the next theorem. Okay, so the statement says angle in a semicircle is a right angle. In order to understand this particular theorem, let me take this diagram. Okay, so this AOB is the diameter of this particular circle, and we know that this diameter divides the circle into semicircle, right? Okay, so angle in the semicircle is a right angle. So in this upper semicircle I have chosen one point C, okay, and if I join all these vertices, that is ACB, then this angle has to be 90 degree. That's what is the meaning of this particular theorem, that is angle ACB is 90 degree. Alright, now let's move on to the next very important, that is the sum of the opposite angles of a cyclic quadrilateral is 180 degree. Now the very same statement can be stated in another way, that is the opposite angles of a cyclic quadrilateral are supplementary. Supplementary angles means pair of angles whose sum is going to be 180 degree. Alright, now in order to understand this, let me take this diagram. Okay, now there's a word called cyclic quadrilateral. Now cyclic quadrilateral means a quadrilateral, okay, and in quadrilateral we have got 4 vertices, right? That is A, B, C and D in this case, A, B, C and D. Now if all the vertices lie exactly on the circumference or the boundary of the circle, then that kind of quadrilateral is known as cyclic quadrilateral. For example, in this case all the vertices are exactly lying on the circumference, right? That's why this ABCD is known as cyclic quadrilateral. Now according to this, the opposite angles of the cyclic quadrilateral are supplementary. That means the opposite angle of B is D, right? So that's why the sum of angle B and D will be 180 degree. Similarly, the sum of A and C has to be 180 degree. So that's what is the meaning of this particular theorem. Okay, now let us try to understand this theorem. So the statement says an exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Now you are quite familiar with something called cyclic quadrilateral. That means all the vertices of the quadrilateral must be lying in the circumference of the circle in case of cyclic quadrilateral. Okay, so that's what I have done. So there's a quadrilateral ABCD whose all vertices are lying exactly on the circumference, okay, and I have extended one of the side, that is AB. Okay, so AB is extended till E. Fine. Okay, now the exterior angle of a cyclic quadrilateral. So exterior angle means this one. Okay, so this is called exterior angle, and this exterior angle will be equal to the interior opposite angle. Now interior means there are 4 interior angles. Okay, so the interior angle here they are talking about is this go to the opposite side. Okay, so this will be lying in the exactly same line, right? So from here the opposite is this one. Okay, so that means this angle and this angle both are equal according to this particular theorem. Okay, so let me repeat once again, this angle and this angle will be equal. Okay, so we have angle CBE, that is CBE is this angle, and ADC, that is ADC, that is this angle. So this angle and this angle will be equal only in case of cyclic quadrilateral. Okay, now with this we'll move on to the next theorem. So the next theorem says the tangent at any point of a circle and the radius of a point are perpendicular to each other. Okay, to understand this particular theorem, we will take this diagram. Okay, so this is my circle with center O. Fine. And I have drawn one tangent AB at point P. And we know that tangent is drawn only at one point in the circumference. We cannot draw one tangent at more than one point. Okay, so we have got AB as the tangent at point P on the circumference of the circle with radius OP. Now, according to question, this tangent and the radius through the point, that is from this point, if I draw the radius, that is OP, they are perpendicular to each other. That is OP, that is this is perpendicular to AB, that is tangent. So that's what is the meaning of this particular theorem. Now let us move on to the next one. So next theorem says, if two tangents are drawn from an external point to a circle, then the lengths of the tangent are equal. Okay, so let us try to understand this using this particular diagram. So there's a circle and I have taken one external point. External point means outside the circle. So P is the point which is lying outside the circle, right? So from P I have drawn two tangents. Okay, so one is this tangent, another is this tangent. So this tangent is touching the circumference at A. Okay, and this tangent is touching the circle at B. Okay, now according to the theorem, the length of the tangents must be equal. That is PA and PB must be equal to each other. That is AP must be equals to BP. Alright, now let us move on to the next theorem. So next theorem says, if two chords of a circle intersect internally or externally, then the product of the length of the segments are equal. Now in order to understand this, we will take two diagrams. One is for internal. Okay, so two chords are intersecting internally here. Okay, so one of the chord is AB, another chord is CD. Both are intersecting at point P. Alright, now let's move on to the next case, that is external case. Now in this external case, this AB and CD, remember AB and CD, AB, this AB, CD and CD represents your chords. Okay, and here they are intersecting internally, and if I extend these two chords, they intersect externally here. Okay, so that's why this is the case of external. Now they are intersecting at point P. Here also they are getting intersected at point P. Alright, now according to the theorem, it is said that the product of the lengths of the segments are equal. Okay, that means PA. Okay, so in both the cases it is valid. So PA is this one, right? So PA into PB. Okay, PA into PB must be equals to PC into PD. So that's what is the meaning of this particular theorem. Alright, now let's move on to the last theorem, that is this one. So the theorem says, if a chord and a tangent intersect externally. So let me take the diagram here. So chord AB and the tangent, okay, intersect externally at point P here, right? Then the product of the length segments of the chord is equal to the square of the length segment of the tangent from the point of contact to the point of intersection. That means they are talking about this. So let's understand it again. Product of the lengths of the segments of the chord, okay, that is PA, that is PA and PB. Okay, PA into PB will be equals to PT square. So that's what is the meaning of this particular theorem. Alright, now with this basics, we'll move on to the problems on circles.